So the theme is I'm continuing symplectic geometry, a little bit about introduction. And Hamiltonian stuff. Mechanics. And of course, this is continuing from last time. So last time, I was doing an example of the so-called linear theory. And that is the case where, say, W omega is a symplectic vector space. So it's a linear setup. And I commented that there exist Lagrangian decompositions I actually didn't prove this, but I will give it as a homework exercise with hints. It's easy to prove. W equals Lagrange and actually a complementary subspace which you can identify with the dual. So what this says is that W omega is just, if you take appropriate basis, is just the standard symplectic space. So there's a change of coordinates to put the symplectic form in standard form, and that means in coordinates of the standard coordinates of R2n. The symplectic form, I wrote down last time, it's X transpose J, X, J what? Now maybe we should even use physics letters, so X should be Q1 through Qn, P1 through Pn. So sometimes we'll write this as PQ. Okay, so and J, of course, as you know, but I'll write it again, J here is 0 minus the identity. Okay. So that's the setup in the linear theory. That's the setup. Now, I derived some things and some of it was homework and so on, but we have the following proposition. If F is the standard mapping from the smooth functions on R2n now, the standard setup, to the vector fields on R2n, is given as usual, just let me remind you, by a Hamiltonian function is mapped to a Hamiltonian field. Hamiltonian function here in the functions to a vector field here, where defined by contraction of the form is DH. This is the mapping, I call it F, and maybe if you like to think what F I have in mind is the field mapping, which associates a field to a function. So you take that field mapping, then the following are equivalent. So, we've talked about this. H is a quadratic form. So the simplest case, which is really very much the physical case, so a quadratic form. So let's even say defined by a symmetric matrix. Say S, which is the form B. No, sorry, I want to get the letters going here. A, B, B transpose down below, C, no, D down here, to be consistent, D. With A symmetric, of course, and as well as B and D symmetric. You're given a Hamiltonian defined by a symmetric form. Let me remind you what I have in mind here. This means Q, P, transpose A, B, B transpose D, Q, P. This is the form. And maybe a half. This physics 1/2 is very good for notation. This is H equal Q.
How do you define the Hamiltonian function?
What?
How do you define the Hamiltonian function? I was not, maybe I didn't get it.
It's a function.
It's just
Smooth
a
function.
And what
That's right. That's a very good question.
May I ask a stupid question?
Well, let's make sure the question is answered. So, are you going to remember your question?
Yes.
Good.
Right.
Okay. It's a very good question you asked. These, at the present time, a Hamiltonian is any function on the manifold, any smooth function. However, in physical situations, and these things are called, physicists call these things observables. And however, in any realistic physical situation, the space of observables is much, much smaller. So it's a reasonable question, okay? And in quantum mechanics, you want to quantize these observables somehow. And in order to do this, in some sense, you have to cut down the size of the observables to a very small thing, about in half. But right now, it's just any function. Okay, but it's a good question. Okay, now your question.
My
Remember.
question is the definition of quadratic form.
Yes. So, quadratic form. Is you start with a bilinear form. So quadratic form on a vector space. In this case, over the real numbers. So you start with a bilinear form over the real numbers, and the associated quadratic form, say of the variable x in coordinates for this vector space after I've taken the basis is b of x. And by the way, I really think about it that way. It might not be positive definite, but I think about it.
But this is not norm, not necessarily norm.
I allow norms to be negative. Okay? So quite often this, maybe I will write here ABC for the signature of this norm. A positive eigenvalues, B negative, and C degeneracy. But it's too much. So let me just emphasize, okay, possibly not positive. And you know, if you have a quadratic form, it's defined by a symmetric matrix, right? I mean, right? So a quadratic form, just to make sure we're talking about the same thing, is some aij xi with xj. Right? And of course, xi xj is the same thing as xj xi, so this matrix can be taken to be symmetric. Okay.
But in definition, B is just bilinear. This is bilinear form.
That's right. So that's what I mean. So B is bilinear form and Q is the associated quadratic form. And as you know, it's trivial to go from bilinear form to this, but you can go backwards. Given the quadratic form, you can obtain, you know how to do that, right? So it's just, as you just pointed out, it's any bilinear form. But I'm interested in the quadratic function. Because we're dealing with functions, that's what Mihai was asking about, we're dealing with functions, and not bilinear forms. So we're really dealing with second order homogeneous polynomials. Homogeneous polynomials in the Greek too.
But if you don't start with the symmetric matrix for B, then if you go to Q and you go back to B, you'll not get the same bilinear form. If you don't start with the symmetric matrix.
That's right. That's right.
So you,
That's right. Anyway, I always start with symmetric matrix. The funny thing is that, so that's the first thing, so, but I'm very pleased that you asked all these questions. The second thing is that you will probably be able to tell me with certainty because you did the homework exercise. Second thing is that XH, so the field associated to H, is a linear field. And a linear field means, at least in my lingo, the ordinary differential equation is of the form x point equals a matrix times x. And that means, in our case, here, x is PQ, so it's using column vectors or QP, so it means Q point, P point is a column vector equals a matrix times QP. And we could derive this matrix immediately, but you probably have it in front of you with your homework. I think M, so I should know what M is along the diagonal. I hope M in the diagonal is B minus B transpose. And
minus
probably,
AD.
huh?
Minus AD.
Where's minus AD?
Minus A is in the right corner and D is below.
Thank you, that's what I was thinking. Yeah? That's what you just said? Yeah. Well, you just have to do it out, and you did, and you know it. So this matrix has obvious conditions. Well, I again reiterate this. B is arbitrary. And A and D are symmetric. And matrices of this type so the set of all matrices matrices of this type is obviously a vector space, a real vector space. And this real vector space has a name. It's called, this is German letters, SP2N. Well, the matrices are 2N by 2N matrices, so that's the reason we call it 2N. And closely related to all of this symplectic geometry. And the key is that this is a Lie algebra. I have to tell you what the bracket is, but the bracket is what you expect. Just the bracket. The E2 is again still in SP. So this is what we call a Lie algebra. It obviously satisfies the Jacobi identity. This is a Lie algebra. So this is the so-called symplectic Lie algebra. And as you see, it's a very simple-minded Lie algebra. I mean, what do you have to do? You have any arbitrary matrices along the diagonal, B and minus B transpose, and then symmetric matrices offhand, and it arises in the way, this is equivalent, the quadratic Hamiltonians. I mean, you should really think physics, because almost all Hamiltonian systems you begin with in physics, harmonic oscillator, anything you begin with is quadratic. It's really quadratic. It's very unusual to go to a higher order step. Yeah, you have this kind of thing. It's a symmetric matrix. You write it down. You go to the Hamiltonian flow, the linear field. It's very simple. It's just matrices of this type, which is a Lie algebra. This is very interesting. Related to a symmetric matrix, the symmetric matrices of those in the symplectic algebra are these. Okay. So this is the symplectic Lie algebra. The third condition is, and this is almost exactly in the homework, but not completely, but you can easily check it yourself, is equivalent condition is the one parameter group which solves this ODE e to the mt. So this is the one parameter group which solves this thing, is contained in the group of symplectic isomorphisms of the standard form under consideration. So I'll write this down. So I should do my best to do some sort of didactics. Symplectic isomorphisms in this group. Let me write it down. SP2NR. And by the way, just using letters, anytime you see a group of this type, then there will be an associated Lie algebra, and will be written in German letters. This is a very standard thing. You have a group, and then you have a Lie algebra. This is the Lie algebra. I could talk about that for a long, long time, but just right now, this is the associated group, and this is the group of transformations. Now I'm going to have a bad letter, but I'm lacking in letters, so let me see here. A, B, C, D, E, F, I don't like G, H, no, I, no, J, no, K, not so good, L. So the group of L, this is not Lagrangian. All right, set of operators L in GL2NR, so that the symplectic form is preserved. L X L Y equals omega X Y. All, I won't write it for, well, okay, for all X. So that is the condition. L, this linear operator is in SP if and only if X, let me write it down, LX transpose J times LX, it's enough to satisfy the norm equation, equals X transpose JX for all X, and that is the statement if and only if, I turn this around, L transpose J L is J. So this is the defining equation for the group. You see? Defining equation for the symplectic group. So the statement is that something is in the symplectic algebra if and only if the one parameter group is in the symplectic group. Please look at this. This is the key symmetry group of the whole thing, the symplectic group. But this is a highly nonlinear equation. You can write it down, but it's a quadratic equation, and in some sense a pain to understand. But these equations here for the algebra, which somehow you go back and forth all the time, these are elementary, very elementary linear equations. That anybody can understand. You understand this quadratic. I have to I have a matrix, transpose it, multiply it by J, multiply it by the matrix, and I'm supposed to get J. That's 4 equations, they're all nonlinear. Right? 4 block equations. Right? You see what I mean? I don't have to do it. Are you going to make me do it? No. So that's not linear. So it's much better if you can get away with it. It's much better to operate in the symplectic algebra, where the Hamiltonian field is defined. Okay. So last time I did an example. I'm just reviewing still, where these equations are easy to understand. If for n equals 1, then the symplectic algebra SP, what's SP2R? It's just the trace field matrices. And the symplectic group is just the matrices with unit determinant. So that is that. Now, I would like to make a remark that you will hear in every physics lecture on this subject. One looks for invariance of the Hamiltonian flow. So the remark is, and let's say EG in the one for n equals 1. Area is an invariant of the solution of any solution of the Hamiltonian equations. And this, I think, was discovered by Kepler, because Kepler understood the two-body problem, and you see there's certain things there where there's a unit of area. There's some sort of cross product in R2, R3. And he saw some invariant, which is an area invariant, but here you see it's completely obvious what that is, because don't forget what omega of a vector A, B, and another vector C, D. All right, this is the standard omega in 2 dimensions. Well, we can do it. I hope you can do it. It's AD minus BC. This is what it is, and you can write it down. And I hope you see this is the determinant. And you see what this is this is the AB and CD. And of course, this is this area, unit of area of that parallelogram, right? The area of the parallelogram is that determinant. And that means that if you're traveling along on this flow, e to the mt, you see this is a flow by symplectic transformations. So that if you have a unit, a thing of area here, you will push it around here. You might change something here, but the area itself does not change because it's a symplectic flow. You see, omega is the usual area form on R2. It's a volume form on R2. This is the advantage, everybody understands it. It's the volume form on R2, it's area. So you read in the first book of mechanics, area is an invariant of the Hamiltonian equations. Oh, it's very nice. You're looking for things that are invariants of this physical system. Area is one. Okay. Yeah. So that's good. And then we did this example. So I did make the remark. I'm just still reviewing the remark. It makes sense to try to diagonalize M. So M will always be this matrix, which is the linear field. Why is that? Because you see, why is that? So if you have V, so that M times V is lambda V. So we have an eigenvector, say some eigenvalue not zero, then E to the MT times V is just the power series, M T to the K over K factorial times V. And of course it's an eigenvalue, so it's lambda, so it's equal to E to the lambda T times K factorial V, right? So, yeah, so, I mean, this really is a very understandable thing, and so we look for diagonalizability, but the key remark is here, is the diagonalizability is a bit mysterious. By the way, I want to emphasize that try to diagonalize. This means you change M by a symplectic transformation, L. So for L in the symplectic group, and it does not change anything in your whole program. It is effectively a symplectic change of basis, so it really changes nothing. And so this is the question we're looking at: how to diagonalize the matrices. And that's what I talked about at the last part of the lecture last time, is the picture of, well, SP2R. I suggested you take a basis, an orthonormal basis with respect to an obvious trace form, which was this, I suggested last time. These physics matrices. This is what I suggested last time. Every physicist will suggest this. And if you draw a nice picture, and I probably won't be able to do it very well, but there's a cone here, which is defined, I'll define it in a minute. So the invariant the action SP2R on SP2R. So here's the picture of the vector space SP2, the German vector space. So we're talking about this action I just wrote below. So M gets mapped to L and L transpose.
minus 1. L minus 1, not
Transpose. Oh, L minus 1. I don't know why I wrote that. Thank you. Fortunately, I wrote it correctly. But this invariant is, I like to take it the 1/2 the trace norm, which is a determinant. And if you use this, or this is the above basis is an orthonormal basis. So this form becomes in coordinates. This trace form, the trace form is the form is equal to x1 squared plus x2 squared minus x3 squared. Form of signature 2, 1, and the interesting thing, now this is really interesting now, is that the orbits inside the light cone, see, the orbits inside the light cone look like satellite dishes looking for television coming from the United States directly above. Yeah. And also down here, these are dishes, and the ones outside, I don't know, maybe I'll take, maybe this will look like this. This is what I talked about last time. Everything on the boundary of the light cone, they're not diagonalizable, but almost everything as usual is diagonalizable, but to two different places. I usually like to take diagonalizable to this place. So the point here, the points here will be lambda times this matrix. So this is diagonal over the reals, and the points here will be lambda times this matrix, which of course has purely imaginary eigenvalues. So, and you can see with higher dimensional symplectic algebra, you will have many such possibilities. They come in pairs, so you either have two real eigenvalues here, two more there in blocks, two there, two there, two there, and then you have some imaginary ones too. So you have different cones depending on whether you have pairs of real or imaginary eigenvalues. Okay? So it's very interesting. There's not just one diagonal matrix, there are two types, either over the reals or over the complexes, plus minus I times purely imaginary or purely real. That's the setup with the symplectic Lie algebra. And that's then how your dynamics is going to be understood, because you're going to look at e to the mt times an eigenvector. Of course, lambda could be imaginary, so you have to understand what that means. And then, of course, you can understand the dynamic. Well, that's then a review of the last time. And let's start with something now. So I want to go to the general case now. Which is extremely beautiful mathematics and puts a huge amount of physics in a nutshell, but of course we use all of this mathematical formulation. So the general setting so we can start fresh, m omega. Okay, this m is now a manifold. This other m was matrix. M omega is a symplectic manifold. Okay, and then I started to tell you at one point, but then I've gotten sidetracked through this linear theory, but I think it was well worth it. I started to tell you, and now I'll tell you in detail about what I like to call the fundamental exact sequence. So I'll write it down and I will tell you about each ingredient of this exact sequence. It's a good way to keep everything in your mind. The exact sequence will be this. I will tell you what this is. By the way, this manifold, unless I say something else, will be connected. And so I'm going to tell you right off the top, so you know what the smooth functions are. These are smooth functions. So let me even write here the smooth functions, so that you have the ingredients here in front of you. You know this, but it's nice to see it again. These are the smooth functions on it. This is what Mihai was asking. What are the Hamiltonians? Any smooth function. And this is just the constant functions. That's the reason I took the thing to be connected. And this is the basic Hamiltonian map, which associates, I call it script F, associates a field to a function. So we've already discussed this. However, I have not told you what the image is. And the image will be a certain space of vector fields that is distinguished. And these vector fields I'm going to call the Hamiltonian fields. And the way I've got this set up, the Hamiltonian fields, this is not going to be the image of this map. You're not going to get all these so-called Hamiltonian fields in the image. There will be a topological obstruction for getting them. There's a map here, which deservedly is called contraction again, to the Durand cohomology, the first Durand cohomology. And the image of this map is the kernel of this map, so I will have to tell you what that is. And in fact, this map is surjective. So this is the setup. Please, if you're in mathematics, get used to this exact sequence language. I don't know if you had that much experience with it, but it's standard. And it means, so I'll just remind you in case you're, boy, this is Roram. So exact, again, say what it means. It means you have a map, you have alpha, beta, and it means the image of alpha is equal to the kernel of beta. So you're discussing, as you move along the sequence, you're discussing every image and every kernel. That's very important, because you're seeing what happens. So let's start looking at what all these letters mean, and then I will explain exactly all the maps. Okay? So I think everybody understands the constant functions. Everybody understands the smooth functions. Now I have to tell you what are the Hamiltonian fields. Well, so the Hamiltonian fields look like this. So X is just some vector field. Some vector field is a Hamiltonian field, so is in this thing I'm called Ham of n, means that the Lie derivative of x of omega annihilates omega. Now let's think what that means. So that means the following. Don't forget how the Lie derivative was defined. So let's look at the meaning. Let's look at the meaning of this. What does it mean, the Lie derivative? What is the meaning of a Lie derivative? You should always write down the definition. Let's write down the definition. And I'm honest to admit, I quite often mess up the signs, but I usually check, so I think we have a place to write it here. So Lie derivative of x of any form, omega. So why don't I just write any form here, beta, equals, you differentiate the form as you move it with the one parameter group by pulling back. Now, if an outside person comes into this room and looks at this stuff and counts and says, you know, these mathematicians are ridiculous because how many letters? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 letters. And nobody understands what's going on. That's just some formal definition, and if you only see those letters, I realize I have many students who listen to what I say and they're only seeing the letters. Really, they're only seeing the letters. You know what I mean? If you only see these letters, you don't understand anything. So you have to have a way to get it into your system. And maybe it's even a way to keep it in your mind and you forget the letters. Right? You forget the letters. Some way to keep it into your body and mind. You feel it here in your stomach. And you see, this is a big advantage I have over you people because I have a big stomach. This is the reason I drink so much wine. Only to have a big stomach so I can get these ideas in you. If I have a form beta, I think this form is living in a linear space someplace, and it is. The space of all forms is a linear space, right? And I push it with a one parameter group. There's some question of sign here, but it is consistent with modern literature to use the sign that I'm using here. I push it to this point with this one parameter group. It's only local, so I really have only this piece. I cannot integrate this one parameter group on this infinite dimensional vector space of all forms. You see, this is inside the infinite dimensional vector space of all forms, so I just push it as a curve. And anybody in his right mind says, well, there's a beautiful thing here called velocity. Right?
Can you please explain how does it act on the space of forms? Because
Yeah, sure.
the push forward acts on the space of vectors usually, but like how does it act on the space of forms?
By duality, push forward, pull back is, we've talked about this, but I'll say it again. Push forward pushes a tangent vector forward, and pull back pulls back a cotangent vector, but that's globally on the space of forms. I think that's what you're asking. Push forward only acts on tangent vectors, right? But if you look at one of my lectures or my notes, I carefully explained, nevertheless, and even though you define pullback via push forward, it turns out to define globally something on forms. That's what I think that's what you're asking. Just check it. Yeah? It's a major difference between vectors and tangent vectors and forms. Because push forward is not defined on vector fields. You understand that, right? Because it's completely clear. You get multi-valued things, all sorts of crazy stuff. But it's defined, pullback is defined on form, and this is this velocity vector here. So this is the lead derivative. You just find the tangent vector. Okay. Now, by the way, I will use later. Okay. Here is a y. Lead derivative acts anywhere you want. Right? As long as what you're talking about, as long as you want, lead derivative acts anywhere. Now, let's talk about what Mihai asked. Mihai said correctly, push forward, you can only do it with a tangent vector, you can't do it with a field. However, if your mapping is a diffeomorphism, then push forward is defined at the level of fields. Right? So if our mapping is a diffeomorphism, and our mapping is here a local diffeomorphism, then I can push forward this thing. So I'll write the whole thing, gx push forward, well no, I should do it by time t, push forward of the tangent vector y is this point here, and I get a velocity vector. And you compute it, and you're sure you know what it is. So the lead derivative of this tangent vector, it's a tangent vector, and the only thing you can think of, you write down, is this. Right? That's the only way you know how to differentiate a tangent vector, but you're wrong. Is this. So it's okay. It doesn't matter, but it's somehow the definition of the bracket. Okay. So I hope it's clear what a bracket is defined there. This is an interesting point.
How do you multiply?
Hmm?
How do you multiply two vectors?
This is exactly why you're right on top of things. How in the devil are you going to multiply two vector fields? Right? Well, it's in the symmetric product, maybe, or the, I don't know. Maybe this is in some tensor product. Yeah, I mean, this is not so bad. I mean, alternating product, maybe.
So that's not the classical lead derivative. Because you said the lead derivative acts on forms.
The leader, then afterwards, I said, a little bit tongue-in-cheek, but a little bit, very seriously, anywhere you want. Yeah? It's completely clear. You have a vector field, you locally integrate it, then you can push things around, and therefore you can differentiate. So anytime you can push something around, you're in business.
But
So-
is it the same thing? It's not the same
I
thing.
just told you, you push it around. But your big debate, which we can have a big argument about, and your first remark is very good, you can't push forward vector fields, and I just did. However, I push it forward with a diffeomorphism. In this case, a local diffeomorphism, what I care, right? So if you have a diffeomorphism, there's no problem pushing vector fields around. It's just well defined. You just push point-wise the tangent vector around. Okay? So this is well defined, and this is well defined, and this is what this is if you define it this. And then again, you made a nasty remark, which is correct. namely, what in the devil is xy minus yx? Okay? Right? Well, there are two answers to that. First of all, I have to tell you how to apply this to a function, right? Because that should be a vector field. Okay? So, I haven't really talked about this, and so I'm happy you're asking. Well, I just apply it. And you still say, with good reason, what the devil is this? You apply y to f, and then you apply x, or you apply x to f, and then you apply y. Right? So certainly that's a differential operator of some sort. right? Because I'm taking derivatives all the time. It looks second order, right? Yes? But if you look at this thing, this is, take a look in local coordinates and see that the second order terms,
If it's smooth, it should
vanish. What?
If it's smooth, they should vanish. If F is smooth.
Yes, everything is smooth here. They vanish. Yes, the second order terms vanish. You understand? You write this one vector field down something and another, and then you just look what happens here, and the second order terms are gone. So this is really a vector field, and in fact, what you can see is, it's very convenient to see.
But aren't all terms second order because you differentiate twice?
No. I'm glad you're asking these questions again. You see, if you think of it in local coordinates, y is some differential operator with coefficients, and the coefficients are non-constant. So when you differentiate with respect to y, you get these non-constant coefficients, and you differentiate them with respect to x. Okay. Right? Okay? That's the point. So, and in fact, you can easily check that the Lie derivative of the bracket is the bracket of the Lie derivative operator. I mean, if this isn't true, then nothing is true in life, and of course, therefore this is true. Yeah, and it's easy to check. Okay?
My initial question was that the first L there on the forms and the L there, they're not the same thing. That's what I see.
They're operating on different spaces.
Yeah, even if you call them the same thing, they're not the same thing.
No. Well, unless you're incredibly abstract, which I am. So, you have an operator Lx. I think you can make this precise. And this is an operator on every space at hand. In particular, given the manifold is fixed. Now, given the manifold, you have the tangent bundle and the cotangent bundle, and the full tensor algebra associated with that. We talked about that, right? All possible tensors, and so on. Well, on that whole thing, this operator acts. Right? It's huge, right? But it acts everywhere you look. It acts on endomorphisms. It acts on,
And if you take the action of Lx on one forms and you identify one forms with vector fields, is it the same action?
how are you going to identify?
Just by duality.
I don't. You have to take a basis. Of course, if you can take the right basis, the answer is yes. But if there's something going on, like a symplectic form, which does identify one form and vector fields because it's non-degenerate, then you're going to have a very nice identification. The answer is yes. Okay, but a Riemannian metric, look, this thing's canonically defined. The identification that you're going to take is always going to be something like a metric, Riemannian metric, or something like this. And then, of course, you can't possibly hope that it's the same thing. Right? But it's a very interesting point. I mean, what is the right identification so that the Lie derivative does the right thing? Yeah. Don't forget that in our bit that there is this formula, which in some sense I try to motivate, defines D. And you see, this is the connection between, well, it's the connection maybe you're talking about. Because on the one hand we have D, so that's on cotangent forms. And on the other hand we have contraction, which is on vector.
But this definition only works for the form. Does it also work for the vector field?
Huh?
I mean, does this definition also works for the vector field?
No, because you don't have D of a vector field.
Okay, so it's very interesting. Your questions I like very much. One way to define D is through this equation. Another way is define Lie derivative. I just defined it here. Okay? No, define D, I'm sorry. It's sort of answering Mihai's question. Define D in some way. Right? One way, if you will see it in some people say D is very easy to define because you just define it in coordinates. It's by Leibniz rule. Right? That's one way to do it, and you prove it's well defined.
That's how all the people do it at the moment.
Yeah, but that's because they're lazy.
You never introduce the pullback of these things.
Yeah, anyway, that's because they're lazy. It's much better to spend a little bit of time thinking, for example. This is one thing you can do. And so, but that's because they're lazy. But then try to prove it's well defined. It's a pain. It's a pain. And if you can't prove it's well defined, you've done nothing because God only knows what this is in general. Right? But anyways, I think we're satisfied with the discussion. We could continue. Yeah? Okay, so this is where I don't even know where I am. So, okay, so the Hamiltonian fields are now defined as those which are preserved by this.
But you didn't explain why they are presumed.
Yeah, okay. So this is the definition, and the definition of the Lie derivative of a form is there, and the little proposition that you can check very easily is that Lx omega equals 0 for any form, so I should write beta here. If and only if G x star T beta equals beta.
It's locally constant, right?
Yeah, the beta is invariant. It's what you think, right? It's constant along the vector field flow. So intuitively for me, it's much easier to understand this, right? The form does not change as you're moving along the flow, but this means its derivative is 0. So, right? And it means if you're moving along the form, moving along this flow just doesn't change. Everywhere it has 0 velocity. So this says that this is Hamiltonian. The Hamiltonian condition, it means, so Hamiltonian condition really means that this doesn't change the symplectic form. So the local flow of the Hamiltonian field does not change the symplectic form. In the lingo of physics, area is preserved. Okay? That's what it means. It is not a theorem, it's a definition actually, because I've defined Hamiltonian that way. But on the other hand, these are, everything that you get here lands here, so I haven't proved that.
Professor, can I ask you something so that
Yeah, sure.
maybe, I want to know if I understood correctly this thing. So saying that the the pullback of the form is exactly as the form, is exactly as saying that the form applied to the push forward of the vectors is the same as the,
That's right.
the form
That's right.
applied to the normal vectors.
That's right.
Is it exactly the same thing?
That's right. And that's the reason this is all the same. We were having a very nice conversation with Professor Schub on this subject, and he knows, of course, basically what's going on here. And he was laughing, saying it's just such a bad joke that you spend all this time in physics with mechanics and so on, and in mathematics it takes about 5 minutes to explain everything. But in fact, and it's true. But on the other hand, look at all this development we really had to do, and the conceptual understanding. All your questions are very good, right? You build this building and you finally understand what's going on conceptually, and then it is a joke. But it takes a while to build the building. Okay? makes, you can have a good time while you're building the building. You know, it's not like a guy out in the sun, someplace in Pakistan where it's 50 degrees, and he's laying bricks here. And no, it's fun building this building. And you learn, and you really develop a lot of conceptual information building it. That's one reason I think it's important to have a course on it. No? Okay. So I guess, let me write, here's the first fact. So I'm talking about this basic sequence here, and I've defined what these Hamiltonian fields are. They're the ones that really are invariant by the local flow. The form is invariant by the local flow, and the fact is the image of the field mapping is contained in the Hamiltonian field.
It comes just from the things you said in the beginning.
Not quite. I don't think quite. Maybe, but not quite. Let me check, and then see if you. Let me check. So let me just write a little proof here. So I have an H, a Hamiltonian, and I associate it to the field, and then I have to check what the Lie derivative is doing. And then I use, in the literature, some people call this the magic formula of Cartan. So the magic formula of Cartan is somewhat, there it is. For me, it's a definition. You will see in the literature this is sometimes called the Cartan formula. So I have to see what this thing does on the symplectic form. So L, now we start going slowly. Omega, let's go very slowly, is contraction of this thing with d omega plus d of the contraction of this thing with omega. All right? I just put omega into Cartan's formula. Now, do you see any vanishing here? So the first definition of the symplectic form is it's zero. So recall, the symplectic form is closed. So therefore, the Lie bracket of this thing, omega, is equal to b.
And that thing, isn't it DDH?
Yeah, and by definition, this thing here is dH, so this is d composed of d of h, which is 0.
But what I was saying is that if you look at the other thing, that the one parameter group doesn't change it,
Yeah.
you just prove that the Hamiltonian field, when you take the
Oh, yeah, okay.
the push forward, it's just in the symplectic
No,
group.
no. I agree completely with what you're saying. The Hamiltonian fields, so be careful. I now see what you're saying. What you're saying is if you take something here, the one parameter group doesn't change, but that says the Lie derivative is 0. But I'm talking about you take something here and you look at its image and you want to prove it's here. I want to prove it's here. I haven't proved it's here yet. And here I proved it's here because when you, okay?
But I just wanted to go back on the track.
Yeah.
On that track. So if you prove that omega of push forward along the field H is
Yeah. Then it's enough.
then it's enough. Yeah.
Yeah.
So
How do you see that immediately?
didn't we prove that it's the vector field of H is in the symplectic group, so that it preserves?
Yes, you're absolutely right. for linear fields. This is the whole discussion at the beginning of the lecture.
Just for leaving.
So that's all we did really, was the linear fields there. So this is the nonlinear version of the first half of the lecture.
Okay.
So in some sense, I'm repeating myself here, but, okay? Thank you. So it's just this using Cartan's formula, so that's that. Okay. And now the question is, what about here? What's the image of this thing? You would like the image to be everything, maybe. So the question now is,
So is that inclusion or?
huh?
What map is that I?
Here.
No. In the exact.
I'm going to tell you now. I haven't told you yet. So now the question is, how about the image? So the image, I have to understand what is the image of this thing. It might not be everything. Might not be, and it is definitely in certain cases not everything. Okay. Oh, how about it? Well, let's take something. So let's experiment. Take X Hamiltonian and ask the question. And ask what is it? Is it and ask is X equal to X sub H for some H? This is the obvious question we have to ask. Let's ask that question and try to answer it. We can answer that question. So,
Can I make a stupid guess? Can I make a stupid guess?
yeah,
Does it have to have divergence 0?
divergence.
Yeah.
It will help to know that, not divergence, but you're on the right track. You will see. I can maybe guess why you're saying divergence. So, the answer is not divergence. So let's just check. So the question is there a function h so that contraction x with omega equals dh? That's the question. Well, let's see here. Lie derivative omega is 0, and that's the same as d of the contraction plus, I'll do it again, contraction of d, but d omega is 0, so this is just d of that. Well, we're almost home. So it says Ix contraction omega equals dh if and only if what?
The one form is exact.
If and only if, well,
It's in the cohomology.
okay, if and only if this one form is exact, what I want to write is here, this one form is closed, if and only if the closed one form, I think that's what you're saying, right? Here the d of this thing is 0, so if and only if the closed one form, contraction x omega, is exact. Right? If and only if it's exact. So we want, this one form, D of this thing here, this thing is a one form alpha, and it's obvious that D of alpha is equal to 0, so it's a candidate for being exact, but it may not be. We know very well examples where you have closed one forms that are not exact, and so what you do is, you say the map iota, here we go, from Hamiltonian to N, goes to Durant cohomology, and is simply, you take a field, and you ask the question, is this one form exact? So you write the one form down, and you write it down in Durant cohomology. And this is a 0 class in Durant cohomology, if and only if this thing is exact, if and only if it's in the kernel of this, and if and only if it's in the image of F. So, that's the reason I called it iota, and your feeling about divergence or something, I don't know, I'm not so sure. This is a topological condition. And you will see, even in simple cases, it's really a serious condition. So, where the devil are, I guess I've erased the fundamental sequence, but let me write it again, and then I'll quit the lecture for today.
But did we study the image? Well, that's interesting.
What?
We didn't say what the image is, did we?
Yeah, it's the kernel of iota.
Oh, okay.
It's the kernel of iota. I mean, it's mysterious, but it's the kernel of iota. All right? Again, so far I've said the Hamiltonian mapping lands in Hamiltonian fields.
So you want to prove that thing is exact, that's what you want to prove, no? You want to prove that thing is exact. That's
Right.
Okay.
So, this sequence is exact here, the sequence is exact here. The last thing I need to show is it's exact here. So the last thing is a little proposition I'll write here below, and then maybe you can prove it. The iota from Hamiltonians, this is very interesting, to Durant cohomology is surjective. This is really very interesting to me. It says you can realize all of Durant cohomology by Hamiltonian mechanics. Isn't that fantastic? I mean, you have a symplectic form. Everything here is realized as an obstruction to the exactness here, Hamiltonian mechanics. Let's prove it. And then I will stop for today. So I have to, you give me a class here. And of course that means that d alpha is 0. And what I have to do is tell you how to get a form. Well, that's pretty easy. I just write alpha equal contraction x omega. There it is again.
And that thing is symplectic, so the space is non-degenerate, so there is
this contraction. I do have this thing, right? Yeah. And that's it.
Can you explain again how y could alpha be equal to the contraction of omega?
Say it again, please.
Y alpha is equal to the contraction of omega. Could you explain again?
Yeah, it's what Mihai just said. Omega is a pairing. Omega is a 2 form. On every tangent space, it's a bilinear 2 form. It's non-degenerate. That means you can view it as a pairing between vectors and covectors, right? Because, okay? A one form, in the sense of at a point, is a covector, yeah? So this says that every one form is realizable by omega as contraction with a field. So don't forget, this is the pairing.
Oh, yeah.
I mean, it's just, it's just you forgot the letters. Yeah. It means to get any one form you want, you just put something in. And this defines a field. But look, d alpha being 0 means that d contraction x omega equals 0. And this, in this situation we've done 100 times, is the lead derivative of zero with Cartan's formula. And so this is the same thing as saying you got yourself a Hamiltonian field. Right? So I mean I can contract and get something good, and I get some vector field, but in fact I contract and get a Hamiltonian field. So it says that in fact everything here is in the image of this contraction map. Everything in Durant cohomology is realized by Hamiltonian mechanics. So this is somehow the easiest way to keep everything in mind. And in my final 2 lectures, I will really expound upon things going on here. Are there other questions? I see you have a question. Yeah.
Did you finish the proof of if there a function h such that the contraction of omega is equal to dh?
Yeah, I think so. Let's see here. Is there a function h so
I
that,
think you only make a sequence of equivalent conditions. That's what
maybe, let's see. So, yes. Oh, maybe I didn't. Oh, I'm sorry.
You have to say that.
Yeah, I'm sorry. I didn't write, I said it, I think, but,
Yeah, you said it, but
so
you already did.
this is the question,
Yeah.
right? So the question is this form exact? Right.
It's in the kernel.
And the form is exact if and only if this I said it, this thing is the 0 class in cohomology, right? So it's in the kernel of that map. Yeah.
Can I ask, why do you always put the zeros there? So in the D sequence it made sense, but in this sequence, I mean,
Sure.
the last map is D,
No, this last map,
to go to 0.
no, it's formal, it's the map to 0.
So you map everything to 0.
Right, and that says that the kernel of this map is everything,
Okay.
and that says that this map is surjective. Okay?
But why do you put 0 in the beginning then?
I map 0 to the 0 element here, and it says that the kernel of this map is 0. So putting the 0 here means injectivity, and putting the 0 here means surjectivity. It's just a formalism, but somehow it's a good formalism.
Okay. I understand.
Yeah?
I still couldn't understand why that equivalence class is equal to 0, which means it's the kernel of.
So the mapping, maybe,
Okay.
The mapping here.
I'm sorry, I understand.
it's a question where you go, yeah, the mapping goes to this thing, yeah.